Okay, so hi everybody. My name is Jim Bagrow. I'm going to be giving a guest lecture filling in for Professor Danforth. And I'm going to be talking about network science, which is a little bit kind of a tangential topic to the traditional dynamical systems, chaos theory, fractals kind of topics. But I think there's lots of interesting connections. And so hopefully as we kind of go through all of the applications and problems in the area, you could be kind of thinking about how do some of the things that we've been studying, how could they possibly be relevant in this kind of an area? A little bit about myself. So I joined UVM in 2013. I'm in the Complex Systems Center along with Professor Danforth. My area is actually originally statistical physics, so I'm very interested in the time evolution of many interacting systems, ensembles, these kinds of things. But I became very interested in networks because of all of the kind of data that was becoming available at the time. So I'm very interested in like algorithms to study a very large data set, statistical inference types of problems. How do you define like a probability distribution over the collection of all possible networks? And I also do a lot of work with data, so studying social networks. How do people move around from their cell phones? What kind of patterns are there? How do we infer activity and predictability amongst friends? Lots and lots of very interesting questions. Not too many that I'll get to in this talk, but we'll see. Okay, so networks. I used to have to really carefully pitch the idea of like what is a network and all of these things. And then Facebook came out, and you can really just say exactly, it's like Facebook. You have your friends, they're connected to you in the social graph, and that is, it's just a prototypical and gigantic example. Facebook is like the monetization of networks. But networks, the way I study them, they're a little bit more abstract. They don't necessarily have to be a social network. They could be a biological types of networks, protein-protein interaction networks, the networks of signaling between ants as they're foraging for food. There's all sorts of possible applications and things. And so you can see here that it's a very, very broad topic. It's almost like an overlay kind of a field that crosses all sorts of disciplinary boundaries, economics, finance, computer science, sociology. There's all sorts of areas where you'll see networks nowadays. So here's my rough plan that I'd like to go through, the kind of history or the origins of networks through some examples of all of the data to try to just, give hints about the diversity of the problems, some properties of networks. I want to talk a little bit about network models. I think that could tie in pretty well to the subject of this course, and also dynamics of networks and dynamics on networks. That fits in very nicely with the whole theme of dynamical systems. And one of my big areas is this problem of community detection. And I probably will run out of time, but we'll see. I have a couple of slides towards the end about that. Okay, so origins. I always like to have a kind of history, and you see a little bit of the people. It helps cement the field, but I'm only going to give two very quick examples. So Euler, you may be familiar with this guy. So he's, one of the most prolific, if not the most prolific mathematicians. He's the guy who came up with the notion of functions, and whenever you write like y equals f of x, that was his idea. It's very, very crazy that you can trace back these like fundamental mathematical concepts to specific people. You can go out and read the paper where somebody proposes the equal sign as a symbol. It's phenomenal. Not this guy. So very, very prolific, just one of these absolute geniuses. And he was very famous as a working scientist or as a working mathematician, traveling around Europe, performing, feats of mathematical daring do. And one of the kind of open challenges that was going along there is this problem called the Seven Bridges, or the Bridges of Königsberg. And so there's a very famous city, at the time it was called Königsberg. And they were very famous because they had these very beautiful bridges, and there were 7 of them. And the idea was that the city would use this as a tourist attraction. This was like their version of Disneyland. And so people would come and they would want to walk on all these bridges and see the city, and it's very fun times. And they had a question at the time, which was, can we figure out the best route for people to take to see all of our bridges? And in particular, they wanted to find a route so that each person could visit all of the islands, all of the different parts of the city, and cross each bridge exactly once. So that way there wasn't any kind of redundancy, there was no backtracking. And so this was an open question, people were struggling and all of this kind of stuff. And Euler came along as a classic mathematician and essentially realizes, Like, there's all of this kind of detail built into this problem, the location of the buildings, the size of the coastlines, the edges of these rivers. And he realized that none of that matters to the question about finding this route between the different land masses. So the key property in mathematics, or the key kind of idea that you always go for, is to abstract away everything that you don't need. Simplify, simplify, simplify. So maybe you make a picture like that one on the right. But in fact, even that is not as abstract as it could be. What you really want to do is think of a picture like this, where you just have these kind of points that represent the land masses, and then these lines connecting them representing the bridges. And when he proposed that idea, the most simplified model possible, it essentially only has the kind of connectivity pattern that removed all of the extraneous detail and let him find out that there was not a path to visit all of the bridges once without repeating. This idea in that picture there is the birth of graph theory. So the entire branch of abstract mathematics came out of this one problem. And a graph is this, if you're not familiar, is this very kind of abstract notion where you have these nodes or vertices that are just kind of sitting out there. They may represent physical objects or have some kind of meaningful representation, but they don't have to. And then there are these links or these edges connecting them. And those two components are pretty much the basic ingredients that would define a graph or a network. I'll essentially use these terms interchangeably. And in this particular case, the nodes would represent those land masses, and each line or each link or each edge would represent one of the bridges. So this is the big birth of graph theory. Another kind of brief application, if you're familiar, which a very, very similar idea, is the four-color theorem. And if you know about this, what this says is that if you have a map, what is the minimum number of colors you need to color all the contiguous regions of the map, such that any regions that touch, any regions that share an edge, don't have the same color. And it's a little bit surprising that as long as you have like a 2D connected map, no matter its orientation, you never need more than 4 colors. So that's the four-color theorem. And sometimes, people will try to come up with very strange examples, but you can work out actually what this that in fact you only need those 4 colors. This is a very interesting proof. It came out in the 70s, I think, originally, because it was one of the first proofs that used computer verification. And the way you go about proving it, which we certainly won't talk about, is exactly the same idea. You take the map and you convert it into a graph where the nodes or the vertices represent the regions, and if they're touching, if they share an edge, then you draw an edge between them. And the idea is that the people who proved the theorem recognized that there are certain repeating patterns, and they were able to essentially enumerate all the possible orientations of connected regions on a map, and then they used the computer to find that you never need more than 4 colors for any of those unique cases. So there have been advancements to clean up that algorithm and so forth. But some very interesting kind of historical examples. But of course, it's a very modern field now, and so we have tons and tons of data. And so what I'd like to do is show a couple of examples of where these networks are showing up. Some may be obvious, some I think may be a little bit less obvious. Any questions or anything like? If you've got any questions, just shout it out. Okay. So a lot of kind of technology and infrastructure, road networks. The power grid is a kind of obvious example. And of course, there's an interesting thing in the U.S. that we kind of have 3 power grids. We have like the Eastern grid, the Western grid, and then there's the Texas power grid, because Texas always has to have its own thing. And what you would do in a system like this is these nodes would represent like the generators, which would be at a very large scale. They would be, these kind of power stations or nuclear plants, these very, very big things. Or they could also be consumers of power, which would be, again, at this scale, they would be like giant factories, manufacturing facilities, or foundries, things like wind farms. And then the links would essentially be these transmission lines. And, you see those lines going all over the country. And what's interesting is that the power grid is essentially something that we created. It's a machine that we built. It works extremely well. It's right up here. It's going 60 hertz. It's just perfectly reliable almost all of the time, unless you have some kind of a, catastrophic blackout. And it turns out that even though we built this system and we understand very well the physics of like the system when it's working normally, when it goes into one of these catastrophic modes, we actually don't have very good physics equations. The DC load flow, the current flow, the laws, they actually don't apply when this thing is undergoing a voltage collapse. And so it's an active area of research to try to predict, the kind of cascading failures and how they might affect the grid at scale. Another example is the air transportation, or you could even generalize it to things like the flow of products being moved, between China and the U.S. and different countries, import, export. And so this is a study where people have been looking at the flow of essentially passengers between airports as they're facilitated by connecting flights. And there's interesting things that you can ask about, for example, a disease outbreak. If some, Ebola breaks out in West Africa, how is it going to spread? And if it spreads through air passengers, it can hop all over the world very, very quickly because we have these hub airports, Atlanta, Heathrow. And once an infected passenger gets to one of those airports, they could go almost anywhere. And if they infect other people, they could spread all over the network or all over the world. And this is very different to if you imagine the spread of like the Black Death in the Middle Ages, which was essentially facilitated by people walking, infected people walking between towns in Europe. And so that kind of spread in these like spatial waves. But now that there is this network connecting these people, you go all over the place, and it's much harder to tease out the origins of outbreaks, and you kind of try to predict the patterns. Another area very interesting is all of this work in telecommunications, phone calls, routing connections between cities and these things. And it used to be that people would actually, they would connect your phone calls manually on these giant switchboards, and eventually that became automated by machines. There's a whole field of mathematics called queuing theory that essentially came out of this. And this is asking these questions about, like, if people are stacking up waiting for their phone calls to go through, what is the optimum way to distribute telephone operators between them, or they could be cashiers at a bank. Lots of interesting results with that. And of course, telecommunications immediately leads into the internet, which is somehow the prototypical communication network. And you can actually define lots of different networks. You could have, the networks between like web pages, which would be the World Wide Web, or you could have the links between servers, and maybe servers are transmitting data. And if you study computer networks and you have all of the, the rules for how packets of data travel around, you can get very, very detailed about these things. So there's lots of different ways, but I hope you're seeing a theme. It's always nodes and links. And really, once you have a problem and you can clearly map those things, then networks become very powerful. And of course, social networks. And yeah, in all of these cases, the idea of a spread of memes or information, there's some rumor. There's a lot of stuff nowadays about fake news and how it's being mediated by social media, all these kinds of things. Lots and lots of interesting questions there. And this is actually a fairly old thing. We would imagine, social networks, that's just part of the human condition, but the field of research you'd think would be fairly recent. But some people were drawing this, you can't see it very well, but people were drawing these kind of diagrams of networks in 1932. So this is a guy, Moreno, who's way, way ahead of the curve of sociology and network science. And of course, there's lots of applications and areas, and there's all these companies. Like I was saying before, Facebook's whole business model is essentially using your social connections to essentially show advertising, but also kind of collect useful information. And another area, maybe one of the biggest scientific areas, is all these biological applications. So I've studied things like protein-protein interaction networks. So you have these kind of lock and key. You kind of work out these molecules. Will they interact or won't they? But then you can look at that at a larger scale, and you could treat the proteins as the nodes, and then links exist between proteins if they interact. And so this is a very famous paper from 2005 that actually pulls out part of this very, very large network of interacting proteins and develops some algorithms to learn these kind of complexes of interrelated protein functionality. And here's another very cool paper about the diseaseome. They always talk about the genome and the connectome. There's a lot of omics in biology these days. And this is a kind of abstract network where you have nodes, but you actually have two classes of nodes. One represents a disease, so it could be something like breast cancer, and another node represents the other type of node represents the genes of an individual. And so one of those nodes could be like BRCA1, which is a gene that's been implicated in a lot of breast cancer studies. and you can actually kind of zoom in and you can see here is breast cancer. Let me try this fancy toy. So breast cancer, and there's BRCA1 and BRCA2. And so a lot of, thank you. It's my latest toy. A lot of research has gone into just mapping out these links because, you know, you can imagine that's someone's entire career, establishing the connection between people who develop breast cancer and people who have that particular gene or not. And then once this has been done at a large enough scale, you can look at this whole network of all of these different genes and diseases. And this is essentially that same network, but drawn without that kind of parallel ordering. So the nodes, I think I can zoom in on this. I have a thing, yeah. So some of the nodes are these different diseases. So these are cancers. And then the little squares are the names of some of the genes. So it has that same structure between the two types of nodes. It's called a bipartite network. And so a lot of people nowadays are studying these kinds of things. Obviously, of course, if you talk about networks, you can imagine like neural networks, meaning in this case biological neural networks. And there's a lot of data now coming out of all of these neural imaging studies, fMRI and all these different scans. We actually have a couple of researchers at UVM who do lots and lots of work on that. I've always found this very fascinating. You know, another area is things like food webs. You can imagine each node represents an animal or a type of animal, a species, and then so this is called a trophic network, which is kind of euphemistic. The links between species indicate the flux of carbon, which is a nice way of saying the animals eat one another. So this is, yeah, rabbits being eaten by foxes. And so you get a lot of structure where you get these kind of base species, which are kind of connected essentially to the sun through photosynthesis. And some animals will feed off of these, and then you get these kind of apex predators that kind of feed on top of these, or sometimes they're called keystone species, although I might be abusing the jargon a little bit. And so you can start to ask questions. If you understand this network structure, what happens if, you know, the fox goes extinct, or if it's no longer in that area? What happens to the food web over time? And with all this stuff about climate change, that becomes pretty serious, actually. And so this is a paper that I actually did a few years ago where we do some, I won't go into the technical details, but it's a way to kind of, like, this is the actual network from the data, and it's very hard to see what's going on just from a picture like this because it's so densely interconnected. You know, we call this like the hairball view or the Death Star view. But we came up with a very interesting kind of spectral representation based on, like, there's a matrix related to this network, and that lets us pull out, like, endangered species, in this case the hawksbill turtle, and separate them from the kind of apex predators in this food web. So lots of very cool stuff. The takeaway is, and this, if you take nothing else, I think this would cover the whole main idea. Networks are this very kind of general purpose kind of playground to be in, and they can represent the connections between people, or connections between computers, connections between proteins, lots and lots of different areas. But at the end of the day, what you essentially have is objects and then relationships between those objects. And that gives us the graphs and the things that we're interested in. Sound reasonable? Okay? Okay, hope some enthusiasm. I think it's pretty exciting stuff. So a good question now is, why would we be interested in studying these networks? What are the kinds of things that we can learn? And the thing that I'm most interested, it gets to this notion of complex systems, is that the individual nodes in these networks may be fairly simple. Not always. I would say people are not particularly simple. But things like ants, or maybe some basic oscillators, some of the models that we'll be discussing, these are fairly simple, and they can interact in somewhat simple ways, but when you combine these simple objects and their interactions, you can get a lot of very complicated or complex behavior, a lot of emergent phenomenon. And I've always found that very, very fascinating. This is one of the core ideas of complex systems or complex adaptive systems. And I think that area is still not very well understood. You know, how simple can things be and still show complexity? How do you define complexity? It's very, very, very wide open. Okay. So as scientists, if we're confronted with these networks, we want to start making measurements. We want to have tools and numbers and quantifiers to help us better understand what we're dealing with. So I'd like to give a brief review of some of the ways that we go about doing this. And some very brief notation. If you're familiar with graph theory, I don't know how many of you may have taken this. It's totally okay if you haven't. But this is, just a basic notation representing, again, those two main components, the nodes and the links. And it's like we really can think of the nodes as a set of, a set called V, and the links as a set called E for edges. And that defines the graph. And another thing that you may want to make along the way is what's called the adjacency matrix. And this is a matrix structure. It's not necessarily the most efficient just in terms of storing data, but it's at least something that's worth thinking about because it connects graphs to, matrix algebra, linear algebra. The idea is that you essentially put a row and a column into this matrix for each node, and then you put in little indicators to say, is node 2 connected to node 1? Here, there isn't a connection between 1 and itself. That would be called a self loop. And so that the pattern of the ones and zeros in that network tells us a lot about the structure of the graph. And if links are undirected, meaning it's not like an arrow, then this matrix is symmetric. Usually call that A. It's an n by n if you have n nodes. Here's the definition. And you can start to talk about things like how many neighbors does a node have by just doing a sum over a row, or if you want, over a column. And that's sometimes called the degree of a node. So we talk a lot about what is the degree of this node. That node has degree 7, or k equals 7, and that means it has 7 neighbors in the network, 7 connections. And yeah, here's like what I was saying. If you want, you can think of a directed network. So this is a case where this node is connected to this node, but the opposite is not the case, whereas here it is bidirectional. And if you want to generalize this further, once you start thinking of a matrix of zeros and ones, what if we allow real numbers or real values to go into that matrix? They could be negative, although typically people think of non-negative values here to build what are called weighted networks. That lets you capture like very strong links. These are very close friends, or these proteins interact very, very easily. These other proteins, it's much more difficult for them to interact, or it's much less likely. And then, yes? So in this case, if you have a directed graph, you have what's called the in degree versus the out degree. So one of the nodes will have an in degree of 1 and an out degree of 0, and the other one will be the other way around. So you can track those degrees separately. In some sense, directed networks are very easy to work from, but in other senses, things can get very weird, actually. You get lots of weird things because of the way things can flow on the network in kind of one direction, but not the other. That can become weird at a larger scale. Okay, so you start talking about the degree. Another kind of useful summary statistic, and this is where statistics in particular comes in, is this notion of the degree distribution. So the idea is that if I look at the whole network and I kind of wear a blindfold and I grab a node at random, what's the probability that it has a certain degree k? That's called the degree distribution. We can measure that by counting up all of the nodes. We can also compute that theoretically in some of the models that we'll talk about. And there's a very interesting kind of classic result with this, which is if you imagine what this thing is going to be like in a network, you would think there's probably some kind of central limit theorem. Most nodes have a typical degree. Like in this case, most nodes have degree 5, maybe degree 4. That's what this kind of picture is showing. And the probability is kind of sharply peaked around that. A couple of nodes have low degree. A couple of nodes maybe have a little bit higher degree. So this is like a degree 2 node, which is what we would intuitively expect. This is the normal distribution that's its name. And it turns out in many, many, many networks, this picture is totally, totally wrong. And in fact, you see a degree distribution that looks like this, which is very heavily skewed to the right. You get these hub nodes way down here that have incredibly high degree that you would never expect in a normal distribution. And then many, many nodes have very, very low degree. And the analogy that I like to give is if this was a distribution of the height of people walking around, this means that most people are 2 or 3 millimeters tall, and then every once in a while there's someone who's 50 meters tall. So there's like 10 people in the US that are 50 meters tall, and almost everybody else is like under a centimeter. So it's very, very different and very counterintuitive compared to the kind of normal probability distributions that we may be used to. And this is a mathematical representation of that, where you have this power law scaling. And I think you've seen these kinds of things when studying fractals, and you talk about fractal dimension and all these things. It's a little bit similar to some of that. Very, very famous paper. And another interesting question, which I've always kind of really focused on, and thought a lot about is that how do you think about a network in terms of space? A network doesn't really exist in a space. You can put it, like a power network or a road network, you can put it in space. But if you think of something like a social network or some of these more abstract things, the gene-disease network, what kind of space does it live in? You don't really measure distances. It's not like this gene is 2 feet away from that disease. So how do we go about thinking about things like distances? And these things tell us how far apart we would want to measure things. So what people typically do, and I think it's actually very interesting, also very classic kind of problems you run into when you take these data structures and programming classes in computer science and basic algorithms courses, you start to think about paths and connections between pieces of the network. So here, imagine I'm at this node, and I want to get to that other node there. So sometimes it's the origin destination or the source and the target. And I would move along the network. And there I've defined a path. And this path is a little bit convoluted because you can see I kind of wandered over here. This is what it looks like when I go driving because I'm always lost all the time. And there are going to be many, many paths between nodes because like you saw those very dense networks, there's just connections all over the place. So you can imagine there's lots of kind of parallel ways that we could go. But one that is typically the most meaningful is what's called the shortest path. There could also be more than one of these, but these are this path. So we would kind of hop from this node to this node and move upwards between the origin and the destination. And you typically would use these to measure distances because the distance could be defined as the number of these hops that you would have to take. The number of hops, the minimum number of hops necessary to go from in this case, I to J. Now, distances also can get a little bit crazy compared to what we're used to with networks. So in this case, what is the distance between those two nodes? There isn't a path connecting these, so it's impossible to get from one to the other. So you can think of that as an infinite distance. And that's actually somewhat meaningful. And this is actually something that's very, very important. So which we'll talk about a little bit more. Networks actually don't need to be kind of globally connected, and it actually tells us a lot about the connectivity pattern if we have these different pieces of the network, which are called components or connected components. So individually, each one of these, which we could think of as a subnetwork or a subgraph, each one of these is connected. And by connected, I mean there's a path from every piece to every other piece, every node. But globally, there isn't any path between these different components. And why did that happen in this network? Why did it not happen in that other network? Those are interesting questions. And another thing that you can start to do with these paths, you can do lots of things with these, but I like this one particular example, is you can start to talk about the centrality, which is like how important are nodes? You would imagine these hubs, remember these 50-meter tall people kind of wandering around, they're very important. They're going to have lots of connections, but that's not the only way to measure importance. Look at this node compared to all of the other nodes. This node here is doing something very, very different from the other ones. And if we think about the paths just traveling between the pieces of this network, I'm going to go from that node to that node and this node to that node. But eventually I'm going to want to, go across the river to the other group. And in fact, if I do that for many origins, there's going to be lots of different paths along that middle piece. And so that middle piece is very, very important. It acts as a bottleneck or a very kind of central bridge. If you think of like the bridges in New York City, if you want to get to Manhattan, or some of the bridges between Cambridge and Boston, those things are very, very important. And if that node or either of these links, if that fell away, if something happened to that, the network would have fallen apart. And that makes those pieces of the network far more important. In comparison, if I delete this node, or if something happens, that person gets sick, or you take a drug which affects the ability of this gene to make protein, that may not have nearly as much of an effect on this network as this one in the middle. Okay, I don't know what's going on there. And this is another kind of example which I'm sure many of you are familiar with, which is PageRank. So this is the classic, this is the algorithm that built Google essentially. Although, to be fair, everybody talks about PageRank still. Google has moved far, far beyond just basic PageRank. And the idea with PageRank is imagine you're essentially moving randomly on a network. In Google's case, they're really interested in the network of web pages that link to one another. And if I move at random for a very long time, where will I find myself going? Will I be on Wikipedia a lot? Will I be on Facebook.com a lot, or Twitter, or whatever the kind of typical websites are? Where will I tend to find myself? And if you assume everything is equally likely and you're just making these hops around, you can actually work out what's called the occupation probability, which is how many times at random, if I look at this random person, will they be at a particular node, which would represent a web page. That's what Google originally used for to help with its search results. It would essentially say that, I think this gets bigger, yeah, that like page B is very important because a lot of people will randomly end up at it. And the way that happens is because you can see it has all of these different links pointing in. So if I'm just randomly hopping around, I'm much more likely to land at a neighbor of B and then go on that link at random onto B. There's some very nice spectral calculations related to the adjacency matrix or another matrix called the graph Laplacian. Very, very cool stuff. Okay. Yeah. Exactly. So clicking on random, imagine that this is a web page and it has two links. And essentially I'm just randomly surfing. That was literally the idea, just randomly surfing along. I may be equally likely to go to here or here, and so anyone who winds up on this page will contribute to these occupation probabilities as they drift to their next visit. And this node benefits from that, not from just this page, but from all of the other pages. So all of those incoming links make it very important. This starts to get at things like hubs and authorities where, this is a very authoritative page because many other people are referencing, many other pages are referencing that page. So, great question. Okay, so another thing, which is something that I like a lot, I have moved more into data as it becomes more available, but I always liked playing with like simple models or mathematical models of networks. So I want to talk briefly about some of the kind of canonical network examples. And maybe you've seen some of these with some of the fractals and things that you're doing. You can make a network that's essentially something like a tree where you just kind of have this recursive division going on, or you could have something like a lattice, or like a chessboard where you just have this grid. Those are technically networks. You wouldn't generally treat them as networks, especially things like the lattice. That's very much a spatial thing, and that's actually been studied for a long time. Lattices and their interplay with like quantum mechanics is one of the foundations of solid-state physics. So when you study crystals, you oftentimes deal with these types of things, or crystalline structure, which includes things like solid-state semiconductors. And excuse me, moving from those kind of very basic, simple structures, which are actually still useful to study because they can be kind of these exemplary cases, you can get into what are called random networks or random graphs, and that's actually a very, very powerful idea to introduce some randomness into the models. We had graph theory very, very long ago, 1736. In order to get to random graph theory, we have to fast forward all the way to 1959, or maybe 58, something like this. So way, 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 much, much, much later before people started to think about what if you have graphs where the connections may be random. And the very famous examples are the Erdős-Renyi network, which another guy, nobody kind of mentions him, but a guy named Gilbert at Bell Labs also worked on that. And there's an interesting kind of dichotomy here because we have Euler, who I mentioned is like one of the most famous of all mathematicians, most prolific. Then there's this guy Erdős, also begins with an E, and it's essentially a constant competition between them, which one ended up being more productive. I think one has published more pages and one has published more papers, and it's like you kind of go back and forth as to which one matters. But both giant, towering, incredibly prolific geniuses. And they proposed essentially the simplest possible model, and it turned out that it shows something very, very interesting. So imagine you have a network where you have a bunch of nodes, say you have n nodes, but you have 0 links. So we would think of that as an empty graph. There are no connections between any of the graphs. And all you do is you look one at a time at every pair of nodes. There's n choose 2 possible pairs. And you flip a coin, and you essentially say, with some small probability p, between 0 and 1, not necessarily small actually, you put a link in between those two nodes. So I flip a coin, I've got, say, a 50-50 chance I put that link in or I don't put that link in. That's one form of what's called the Erdős-Renyi model. And this probability P essentially lets you modulate between a completely empty graph and a fully connected graph, where you have P equals 1. And this very simple kind of toy example, I mean, you cannot get any simpler than this, actually shows something pretty interesting, which is n times p is the average, approximately the average degree of each node. It's actually the average degree is n minus 1 times p. If that number, depending on how you choose p, if that product here is less than 1, then it means the network here will actually be globally disconnected. There will be these occasional edges. You may occasionally get this, but it's very unlikely. And if you have a large network, you're going to have a very disconnected network. At exactly this value, you will start to see large connections. And large meaning that they get bigger as the network gets bigger, as you look at different values of n. And then if you're above that threshold, that particular choice of p equals 1 over n, then you see like a nice well-connected network. And that goes all the way up to p equals 1, where you would have every possible link exist. We will get back to that in a little bit later, but that defines some random properties of the network, and I'd like to return to this notion of the degree distribution. So we talked about this scale-free network where we have these giant hubs, and then we have many people have very low degree. That previous network example, the network model, that won't reproduce that because that essentially treats every node as the same, every possible link is the same. You could actually work out you have a Poisson degree distribution, which does not obey these or display these very, very large hubs. So earlier models, that model has no hubs. So these people came along. They're not the first actually to do this. This is Barabási and Albert. Barabási was my postdoc supervisor actually. So now we have connections to the modern era, or at least the era that I lived through. And they proposed a very, very simple model, which I think is just a genius in its simplicity and what it shows. And it's a growing network model. So it's not like the Erdos-Renyi where you have an empty graph and you're putting links into it at random. This one behaves a little bit differently. You start with some very small network. Could be a single edge, or it could be, in this case, a little triangle. And you essentially, you insert nodes into it one at a time. So you can think of this as like giving birth to a new node. That node is just sitting there. It's just chilling, ready to come in. And eventually, through their model, that node decides to come in and form links to the existing network. So that's called attachment. And that just repeats. You just give birth and you insert yourself. You give birth and you insert yourself. And they proposed a very simple way to do this. Essentially, at each time step, the node comes in and it attaches to m existing nodes, where m is some parameter. In this case, m equals 2. So I'm coming in. I'm new. Hi, everybody. Welcome to the network. I've got these 2 links, and I just come in and I want to attach to existing nodes. That'll make the network a little bit bigger. And here's the clever part, is this rich get richer mechanism, which they called preferential attachment. It's also called cumulative advantage. It's also called the Matthew effect, also called rich get richer. And the idea behind that is you link to an existing node, which I'll call I, proportional to its degree. So the idea, which is what's in this equation, is the higher the degree of that node, the more likely you are to attach to it. So if I have a lot of links, I'm more likely to get a lot of links. And so that's this rich get richer mechanism. And when you do that, sure enough, here's a picture of a very small example that I just simulated. You get exactly this beautiful kind of scale-free distribution. And I've used the size of the nodes to represent the degree. So you can see there's these hubs. You don't get this Gaussian or normal distribution of the degrees. And what they showed, which is very interesting, they showed with simulations, but you can also work out some calculations, is that if you did this preferential attachment mechanism and you did not have growth, like you were just inserting links into a fixed size graph, you would not get the scale-free property. You actually need both new nodes coming in and that rich get richer mechanism, which kind of makes sense because if new nodes are not coming in, pretty soon all those very short people, remember the 2 millimeter people, there won't be enough of them. Those are all the brand new people that just came into the network. And yeah, they're not actually the first people to study this. So there's a very, very famous guy named Herb Simon, a Nobel Prize winner, another one of these genius types. He studied this not on networks necessarily, but just on the probability distribution. And he was not the first person either to study this. Euler studied this in I think the 20s or the 30s. So these ideas are they're recurrent. You know, discoveries are named after the last person to discover them. And one thing that they did, this is in the late 90s, is that they actually showed, what made this exciting is they showed that there were all sorts of new areas where we could see these scale-free properties. So they were looking at World Wide Web data, which again in the 90s was kind of brand new. And there's the example of their model, which I won't go into the details too much. Okay, so let me power through and discuss some of the things which I think would be especially interesting in a course where you study dynamical systems. Because in particular, these networks, they're kind of structural in a sense. Like you're building them, and maybe you have a dynamic process that constructs them, like these models, but then they sit there, and then you want to imagine like what would happen on top of one of these networks, right? The power is flowing on top of the power grid. But except for like building new lines and things, which is very slow, the power grid is kind of a static entity. It defines the structure more than the dynamics. So we'll have some examples here of like network robustness. So maybe you've studied these kinds of things in like stochastic resonance and these kinds of things. The Tacoma-Narrows bridge, where they didn't put channels. I think this was the explanation. They didn't put channels for the wind to go through the bridge, and so that introduced a forcing, like a resonance, and it kept absorbing all that force until the bridge failed catastrophically. So welcome to engineering. Yeah, terrifying. Could you imagine? Oh my gosh. Okay. So this is actually something I've studied a lot for a couple of different reasons, including just measurement error in these networks. This idea of robustness of a network. So you have a network, and you could think of the network as like I was saying before, many simple elements that are interacting in some way. But those elements, they may have some problems with their reliability or their robustness. So imagine if every once in a while one of them fails. Yeah, this is a very famous example of a train that drove through the side of a building. I think this is like a train station up here. I think this is 1906. So this is one of the favorite textbooks I ever had as an undergrad, as an introduction to error analysis. And this is on the cover. So that's an awesome book. So if the individual elements are failing in some way, and there's many ways they could fail, what's going to happen globally to the network? That's this question of network robustness. And this connects to a field in physics and in statistical physics called percolation. And percolation has a very simple idea, and it's got a simple name if you think of like a coffee percolator. The idea is that, imagine I have some soil or something like this that has, it's kind of rocky, it has little air cavities and voids inside of it. And then I want to understand how a fluid would percolate through this. And so the example I'm giving here is somebody pouring water, but the more practical application is oil. You want to understand how oil is moving through, some part of the earth. And the oil, it can't go through the stone areas, but it can go through the gaps. We can make a very, very simple toy model of that, which is this lattice on the other side. So the lattice is kind of an abstract representation of this porous medium, and the links would represent the places where parts of the medium are connected, so you could flow through these things. And then blockages are essentially cuts to those links. The links in this context are sometimes called bonds. And the idea is how many of those bonds need to be cut, or how many blockages need for there to be in order to prevent the fluid from entirely percolating through the network. And we can see in this case that there is like a channel. It's almost like solving a maze. We're trying to find a pathway from the top to the bottom. This also has lots of applications in electrical context, where you're trying to find like, will current flow through this resistive medium? And this notion here is sometimes called a spanning cluster. So it means there's a set of connected components that goes from the top to the bottom. We can generalize that from something like a lattice to a network, where we just have the network, and we just say, and this is the simplest model, we say that each piece of the network, meaning either a node or a link, or maybe both, each piece independently and individually fails with some small probability p. So I've got my social network, and I look at each person, and you failed with probability p, and you failed with probability p. This would harm my teaching evaluations, I think, if I went through and did that. So everybody passes. And then the question becomes, if I'm going into the network and deleting these pieces, what happens to the whole network? Does it become disconnected? Does it withstand this damage and continue working? And instead of thinking of the spanning cluster, because that kind of has this like gravity picture, things flowing top to bottom, we think about, is there a giant component or a giant connected component, which would say, like, is most of the network still connected? Can you still reach most areas of the network? Or has there been so much damage, there's so much things cut out that we can't get from where we want to go? And here's an example, actually, of this. So here's a network. It's got this connected component here. There's a bunch of little kind of fuzz hanging off, nodes of degree 0 or degree 1, these kinds of things. And then here what we can see is this is kind of a progressive cartoon snapshot of more and more damage. So as the network receives more damage, let me use my thing again. Eventually, it completely falls apart, whereas here, completely connected, and it kind of, you can see the giant component like start to erode as more and more damage happens. That erosion process is actually very interesting because it tells us a lot about the robustness of the network. In particular, is this damage, and by damage I mean the shrinking of the connected part. If you think of the large part as the mostly functional piece, does that happen suddenly or gradually? Here it kind of seemed like it happened gradually. And it turns out that in many systems, surprisingly, it doesn't happen gradually, it happens suddenly, where you have a perfectly working system, and then all of a sudden the system is completely broken. So it undergoes what's called a phase transition, or in this particular context, a percolation transition. And here's a cartoon of this. So this is the size of the size of the giant connected component, which is a fraction of nodes that are still connected in that large piece, as a function of this survival probability, which in this case is 1 minus p. And this is kind of a cartoon example, but what we see is that at the beginning, which is in the right corner, the network's completely connected, everything's going great, and then in a very small range, between say 0.6 and a little bit above 0.4, just completely dead. The giant component becomes 0. And that is very, very interesting for the robustness of these types of networks. Also, as you can see, this is very closely connected to that Erdos-Renyi model. So the Erdos-Renyi model is almost like running this process backwards. Some networks, however, are very, very special in terms of how they respond to this damage. So remember these scale-free networks, they have these giant, giant hubs. If I start hitting pieces of that network at random, the hubs are a pretty small part of the network. They're not negligible, but they're a small 1%, 5%. So it's unlikely that if I delete 20% of the links or the nodes, that I will delete every single hub. And those hubs do an exceptionally disproportionate job at connecting the network, right? This one node here connects almost everyone in the graph, and so I'd have to get that one out for sure in order to kill the whole connectivity of the network. And so it's unlikely if I'm just having random failures, it's unlikely that I'll hit every hub, and so it's unlikely that I'll be able to do too much damage to the network. And this is one of the very famous results. It's an immediate follow-up to the introduction of these scale-free networks, which is their error tolerance or their robustness or their resilience. So these are some very, very famous papers. My PhD advisor is on the paper on the right there. And what they showed is that scale-free networks are very, very robust to random failures or random breakdowns, which actually is kind of a good thing because the internet was originally designed for the military to keep talking after a nuclear war. So you would want, if you imagine that the nukes are coming in, if you very casually model that as flipping coins, that would be a good sign that the network is staying connected. The missile silos can still launch. Terrible, terrible examples, but that was what it was like. And so if you look at one of these scale-free networks, you're not going to see a picture here where you survive up until about 50% failures. You're actually going to see a picture more like that. And what this means is you've got to kill off like 80% of the network before you start to notice anything, and then it will finally fail. And essentially, to become completely disconnected, everyone's got to go, at least on average. So that's the definition of robustness. Now, that connects to another interesting question, which is I'm talking about the failures as just this random process. Everything fails with some small probability p. That's not an incredibly plausible model. This has actually lots of applications in things like manufacturing in these areas. But in addition to just there being some kind of bias in the elements that are failing, you can imagine attacking the network. So I understand now that the hubs are very important, so I'm not going to attack the network at random. I'm going to go after those hubs. And it turns out that if I bias myself so that hubs are more likely to fail, the picture completely changes. So in exactly this picture. And it turns out that in that context, scale-free networks, it's like they're almost designed, maybe not quite intentionally, but they're designed to do very well against random failure. The flip side to that is that they're now very, very vulnerable to these intentional attacks. So deleting a small number of these hubs, it does an incredible amount of damage. And so here are, again, some very famous papers, essentially from those same people doing this research. Okay, so yeah, percolation is a huge, huge area, lots of applications. And there's lots more things going on. You can imagine cascading failures to model things like power grids. It's also useful for like sampling effects and measurement errors in networks. So imagine if I go out and I survey people in an office building, and I'm talking to people, and I fail to talk to Bob because Bob is always by the copier and he's never in his office. So I don't talk to him. So it's like I didn't get him in my social network. What does that make my network look like compared to the true network, within that kind of office building? Yeah, and there are lots of other areas where things can map onto this. For example, a disease outbreak or a vaccination. You can imagine that vaccinating is almost like, bless you, exactly on topic. Vaccinating somebody is like taking them out of the network that the disease would spread on, because the disease may be hopping from person to person. But if I vaccinate you, you're no longer able to do transmission, so it's like you're out of the network. So, and that is essentially also a kind of percolation problem, and I think I have some time to get into this. Okay, now some pretty interesting stuff. I know I've been talking a lot about these things, but I think this might start to connect networks to the more traditional dynamical systems that maybe you've been seeing. So dynamics on networks is one thing that you can talk about. Another thing is dynamics of networks, where the network is actually evolving or changing in time. But a very, very simple thing is imagine the network is kind of this static substrate that is enabling some dynamical process. Bless you. And in this context, I'm going to show a little cartoon example, which is little metronomes. So I think you've studied like synchronization and oscillators and these kinds of things. So you can imagine each one of these metronomes as, it's doing its thing. It's oscillating with some frequency. But because they're on a network, you can imagine that they're actually kind of coupled together. So each one of the oscillators has its own intrinsic or natural frequency, but then it feels a kind of a push or a pull from its neighbors on the graph. So maybe, this oscillator is feeling this one, and the neighbor maybe wants to beat a little bit faster, and that may cause the node to speed up a little bit or maybe slow down. And so eventually they may become, they may start at kind of random. They're all bouncing around at different frequencies, but due to this coupling, they may eventually all become synchronized, and they all kind of beat at the same frequency. When does that happen? How does the network affect that? And can you do things like, can you take the network and change it a little bit in order to make synchronization happen more quickly or happen more slowly? So lots and lots of very famous examples. And these things, these oscillators is one particularly interesting example. And there's a huge amount of work on one example of this. It's called a phase oscillator. The example is called the Kuramoto model. Kuramoto was a Japanese physicist. And it is a huge area, and there's, I've seen hundreds of talks on this and all sorts of very interesting things, and Strogatz has studied this problem, if you've seen any of the work that Strogatz has been doing, including on networks. The Kuramoto model in particular is very interesting to mathematicians because it is a nonlinear model, but in certain regimes it is exactly solvable, and that is very, very rare. Typically only linear models are exactly solvable. And that's what Kuramoto showed, and it's a beautiful, beautiful, simple, elegant model. So much fun to play with. And this notion of these dynamics can also connect to some of the examples I was talking about spreading. Imagine there's a disease outbreak or some kind of information cascade. So yeah, you can imagine, the Walking Dead have come in, the zombies. But spreading is actually a very general purpose idea, at least abstractly. It could be things like, the adoption of some kind of products. So, am I going to start using an iPhone? And this is something that, in marketing schools and in business school, they study this a lot, actually. There's a lot of Rogers' law of diffusion and Gompert's law. There's lots of interesting stuff here. And a very simple thing to get to disease models in particular, there's this notion of these very simple epidemic models. Although lots of spreading things don't really behave like diseases, and diseases don't really behave like this. But this is, I don't know did you study like SI models or SIR? Yes, in this class? Okay, so many people haven't seen this. So let me just go in briefly in this. We have a couple of people who know about this. The idea with this, these are called compartmental models. And it is a very, very simple kind of toy model of a population that's getting sick. So the people are essentially in two classes. they're either susceptible to the disease, they haven't gotten it yet, but they could, or they have the disease and they're called infected. So these are the S's and the I's. And essentially everybody is kind of well mixed, so everybody kind of collides with everybody. They're equally likely, so we can treat it as just a kind of continuous process, and we can essentially study what is the fraction of the population in these two compartments and what is the kind of rate, the transmission rate between these two boxes. And you can solve this system, and this is a plot of a population where initially one person's infected, everyone else is susceptible, and then over time, the blue curve is the susceptible curve. Over time, the susceptible compartment empties out and the infected compartment fills up. And you can study this. It's a very classic dynamical system. Then you can make more complicated models. They become more realistic. So this is the SIR model, where infected people, they don't just stay infected forever. Eventually, they recover from the disease. And a recovered person, they go into this new third compartment. They don't get reinfected because it's assumed that they've developed an immunity. Their immune system has caught up. Again, it's a toy model. You can imagine lots of extensions. And actually, real things, I think it was malaria, is actually like a 29-compartment model. So it's very, very complicated. But this is also something where you can study. You can work out some coupling equations under some assumptions. Won't go into any of these details, but this is like the rate of change of the S compartment and the different compartments. I'll skip the details just for time. And you can actually work out what happens. And so in this case, the S compartment, which is the blue curve, eventually empties out. Eventually, the R compartment fills up completely. The whole population becomes recovered. But in the intermediate time, during the outbreak, there's a lot of people in the red compartment, which is the infected. So this is like the peak flu season, so to speak. It's a very simple model. It makes a lot of assumptions that aren't necessarily realistic, but it's actually fun to play around with, and it's informative of a lot of the basics. We can take a compartment model like this and put it on top of a network. So now it's not just people are randomly interacting with one another. They're interacting via, for example, their social network. So this could let us represent the spread of a disease. You're susceptible to the disease, or maybe you're susceptible to a meme, like adopting the use of the iPhone, and then with some rate, people who were susceptible eventually just cave in. Okay, sign me up for the Kool-Aid. I'm going to buy your stupid iPhone, and then you move from the S compartment to the I compartment. I have an iPhone, so. And of course, the thing that's very interesting is, unlike in a well-mixed population, what if the network is disconnected, right? And the outbreak happens in one of those components. There's no link for the outbreak to spread to the other component. So this gets at things like percolation and these kinds of questions. So if that network is disconnected, that affects the severity of an outbreak, sometimes called the attack rate or the attack ratio. I don't remember exactly. Excuse me. And the distribution of the component size is not just a giant component, but all the different components. That tells us, like, what should we expect about how big the disease will be. So the disease is likely to break out in the giant component. It will have this severity, 90% of the network. But if it breaks out somewhere else, it'll be much smaller. And we've had a bunch of near misses lately with like Ebola and some of this bird flu, and there was a swine flu a few years ago. And we've been lucky. We've kind of avoided the outbreak in the giant component, which would be like the whole Earth. We'd be in trouble. And another thing that's pretty interesting about this when you get into the dynamics is that there's other things happening besides just the disease spreading. And remember, the disease is just an example. It could be all these other ideas and things, anything that's spreading. People could be recovering. So I could be getting better. And if I'm getting better faster than I'm transmitting the disease, maybe because I isolated myself and so I didn't want to talk to people, the interplay between those different rates can affect the spread of the disease. So you can think of a transmission probability, an effective transmission probability that incorporates these things. And if the disease does not get transmitted in the time it would take someone to recover, you could think of that as a link that's kind of broken. It's not actually broken, but in the spreading network it's broken. And that brings us back to this notion of percolation. So like here is a network, the one on the right, where transmission is less likely. And so you could model that in a kind of simple way by imagining that some of the links are broken. So if you've only got a 50-50 chance of spreading a disease, you may have 2 or 3 of your links out of your 6 or 7 that are, in this particular outbreak, not available. And that lets us use the percolation calculations that we have to study these the severity of the outbreak. And here is like if the disease transmission becomes even less likely. So that's very cool because that connects the dynamical spread to the structure. And that's a very common idea that people will often do is map the dynamics, which may be hard to understand, onto a kind of auxiliary structure. It's not the original structure, but it's related to the original structure. And that makes it kind of analytic tools, things like this, which are very cool. Okay, so that's what I was saying. So I'll just keep going. And then this is another example which I essentially gave already. You can imagine if a disease is spreading, but I've developed a vaccine, I can start to go out and vaccinate people. And that's kind of like the disease is spreading quick, start deleting all these people because if they're vaccinated, they can't participate in the spread, so it's like they're not part of the network. So that is like a good way to attack the network. I'm attacking the network of the disease, not really the network of the people by means of this vaccination. So I want to vaccinate the hubs. Exactly this same idea. And there's actually a very interesting study. I think they did it amongst undergrads at Harvard. Maybe it was Harvard. And they wanted to see when the flu comes, where do people get sick from? And can we identify that ahead of time? And so they asked people, who are your friends? And the people who tended to be the friends of people, they actually got sick first, which is a little bit weird. And what's happening there is because if you pick a node at random, and then you say, tell me one of your friends, you're more likely to pick a higher degree person because a higher degree person has more friends. So it's exactly that kind of page rank thing. You're next to a hub. And so when you do that, you can actually say that the friends of people, friends of friends, they're more likely to have the disease. So if I want a very simple way, I don't actually know the social network, but I want to start vaccinating people, very, very simple strategy. I say, who are your friends? And then I go and vaccinate them instead of you. And it sounds bad, but that will actually globally have a better effect. So, a very interesting idea. Okay, so I've got a couple minutes left, right? This is 75 minutes, right? Okay, so going pretty long, but I'm towards the end. So I'm just going to talk briefly about this. This is actually an area I've worked on a lot, which is communities or community detection. And the idea is that when you look at a network, there is properties and structures at all different scales. And so I have a kind of cartoon picture of this. So you can imagine very local properties, maybe to an individual node, or very global properties that involve the entire network. And I talked about very, very few of these, but there's a whole sequence of them that network scientists have been studying and developing that kind of span the spectrum from global to local. And one thing that's very interesting is the stuff that's kind of in the middle. It doesn't depend on small parts of the network, but it doesn't depend on the entire network either. These are sometimes called mesoscopic or mesoscale, between scale. And one of them is this notion of modules or modular structure, or what is more commonly called communities. And communities are a very, very intuitive kind of a notion. So here's a network that has some modular structure. And I've colored the nodes to actually represent the modular structure. And these modules are areas that are kind of more densely connected. There's lots of links over here. There's lots of links here, but there's not so many links between them. Does anybody recognize this network? A little bit surprising, actually. This is another example of how abstract these networks can get. This is actually the college football network, NCAA, I think Division I. And each node actually represents a team, and the teams, they will play against one another. That's where the links come from. And this modular structure comes from the conferences. There's like, I'm not really a sports guy, like Pac-10, Big East, Big Ten, Pacs, I don't know. There's, if you're familiar with this, there's these different divisions or these different conferences that they play in. The reason is so that the players aren't really traveling so much. And these nodes here are the independent teams, like Notre Dame, I think Army and Navy. Don't they have whatever. There's a couple of teams that aren't in these conferences that behave a little bit differently. And those conferences introduce a kind of modular structure. Did you have a question? You mean in terms of the picture? So the picture, there is a whole field of like graph visualization and how do you draw these things pretty well. I've used an algorithm that lays them out to highlight the structure, but in fact the structure should be defined based on the connectivity, not based on these distances. Now, there's a relationship with distance in the sense that these colleges are at specific locations, and the conferences tend to be geographic, but that's not really shown here in this picture. So, but yeah, that's a great point. Okay, and here's a slightly simplified cartoon I took from a paper that really highlights the idea of this modular structure is that there are these groups within the network that have lots of connections inside the group. These are the blue links. Excuse me. Disease outbreak. And then there are connections across the groups, which are the red links, but those are much less likely, much less common. And so that defines the structure. Internal versus external links. So you can think of this as like high density regions, low density regions. And then the problem, which is a very interesting one to study, is that when you're given a network, you don't know the groups, you just have the network itself. And your job is to essentially find the groups. So starting from this, you want to do something like that and actually find a way to take those nodes and place them into the groups. And you want to say, you know, is this a good division of these nodes or a good partition of these nodes, or is it a bad partition? So that's the community problem or the community detection problem. It's essentially a kind of structural inference. You want to learn these groups when you didn't know them beforehand. And sometimes it's very straightforward. This also gets to this question about the picture. Like here, it's very clear what the groups are. Again, I put the colors on. The network on the right, it's not nearly as clear. That network actually does also have a meaningful community structure, but in the visualization, you just can't see. Again, you're in that Death Star hairball kind of a situation. Now, forget about that network. What about this network? So, and this is a real network, and it has a real community structure, and you'd never really be able to see it from this picture alone. So, lots and lots of applications for things like load balancing. You want to have, if the network represents like data being transmitted between computers, you want to find as many connections in like nearby areas of the computers because the data will transmit more quickly. Things like disease spreading. It's also huge. We actually saw this before about learning about related functionality of proteins. You know, the problem that the biologists have is there's many things going on in the cell that are not well understood. What is this thing doing? Well, let's look at the related stuff. We know what they're doing, so maybe it does the same thing, or it's related in some way. So you can learn like functional modules, or sometimes these are called complexes. And the kind of just the general purpose thing is you're learning with this problem, you're learning a new kind of relationship. We have the relationships that are the links, but now we can say these two nodes have a relationship, they're in the same community, they're in the same group. And that is actually very useful information. Okay, and I won't go, let me just go back very quickly. I should have a picture of this, but I guess I cut it out. This is actually a network of word associations. So I play a game where I say, here's a word, and you think of the first word that comes to mind. So I say cow, and you immediately say milk. Or I say milk, and you immediately say cheese. And so it's the network of related terms. And the thing about that is that many words have multiple meanings. So if I say the word bright, you may be thinking about like sunlight, very, sharp light, seeing large things. Colors, you may be thinking about intelligence. That's a very bright student. And so many words have many meanings. And so you don't get these kind of disjoint groups. You get a lot of overlapping and interconnected groups. And so there's a huge amount of structure lurking in this picture that you would never see. Okay, let me go forward. So I should have had another slide to show that. Okay, so the takeaway, so this is how I'm feeling. I don't know if that's how you're feeling, but I'm feeling that. This is kind of the rough picture of what I discussed, and I actually got to most of these things, including the communities, which I was worried I'd run out of time. Now, network science continues moving forward. There's tons and tons of research areas and problems. I think it remains totally wide open. It's not as easy as maybe in the 1990s. There's tons and tons of questions and things. So if you're interested in learning about this in particular is something I'm very interested in. What if the network is changing over time, or what if you have a dynamic process that is changing the links? So for example, imagine a social network or a contact network. A disease is spreading, but then people are like running away from the disease, like, oh my God, I'm going to, barricade myself in the home, try to not get sick. That's changing the links in response to dynamics nearby. Totally wide open area, very little models. There's very little mathematics that can help with that, so it's lots of simulation studies. Very, very interesting questions there. A lot of people are studying things about controlling networks and the dynamics on top of networks. So if you're interested in things like control theory, networks are always a part of that. Network medicine, we've been talking about this, the diseaseome, that lets you essentially define like potential drug treatments. Like we want to, affect these genes that maybe are influencing these diseases. So maybe we can tailor certain drug regimes. And then you get into very fancy things like layered networks and networks that contain networks inside of them. And that gets a little bit crazy. I find personally this is too much for me. A lot of people are doing super cool stuff in this area, but I'm still working on single networks. So, okay, I needed to have one really cheesy transition. So thank you very much. So if you want to ask any questions or anything, I can stay. We've got a few minutes left. I guess I'm supposed to collect your homework, so I should probably, not put this in the recycling bin. But if you haven't brought your homework up, you can just bring it up now, I think.